Okay, so in the last class we were discussing about the internal architecture of the PLC. Now a little bit more about the different units inside the PLC. So first of all, the central processing unit, as it was mentioned also in the last class, that the CPU contains the microprocessor and all the controlling process or controlling signals are carried out by the microprocessor. And the internal structure of the CPU depends on which type of microprocessor is used or which model of microprocessor is used. Now, inside the microprocessor, there is an arithmetic logic unit in order to carry out the data manipulation or the arithmetic or logical operations. Now, apart from that, the microprocessor also contains some internal registers, some internal memory locations that are used while executing the instructions. Now, the different types of buses were introduced in the internal architecture, in the diagram of the internal architecture. So 4 types of buses are normally there. The data bus, which carries the different data from the input device, or any data that is processed by the CPU is carried through the data bus. The address bus carries the information of the memory locations, the addresses of different memory locations. And the address bus are used to send or indicate to desired location for reading or writing a particular data in a memory location. The control bus sends different controlling signals to the other units, different memory units, the input-output interfacing units from the control bus. The CPU sends these signals. And the input-output system bus, I mean, they are responsible for establishing connection between the input-output module and the external input-output devices, and also the programming device that is used to write the program into the PLC. So for those communications, the system bus is used. The memory units, normally they are divided into 2 parts, the ROM and the RAM, the read-only memory and the random access memory. So maybe most of you know these things, that the ROM is the memory location where the user doesn't have any authority to change anything. The manufacturer provides or stores the operating system and some fixed data that the CPU can use as per the requirement to execute a certain instruction. Now, the ROM, the data which is stored in the ROM, if there is some power failure or power interruption, or if no power is supplied to the board, still the data which is stored in the ROM is it is not erased, it is kept intact. Now, EPROM is a sort of a special type of read-only memory which gives the user to store some information or some program permanently until the user decides to erase them by themselves or intentionally wants to erase them. So in addition to the ROM, sometimes the EPROM is also associated by the manufacturer, so that the user can store some program, so that program doesn't have to be burned to the board or written each time the user wants to execute that program. So this EPROM can be, this erasable and programmable read-only memory can be often used as a backup for a program which is developed in the RAM, so that program can be stored until the user wants to erase it by himself. Or okay, so the random access memory, it is the portion of the memory that is accessible by the operator or the user in order to read some information or write some information into this particular portion of the memory. And it is also divided into several segments. For example, a portion is allocated to store the instructions of the program only, then some portion is allocated in order to store the different data, and some memory locations are also separated for the timing, data operations, or the counting operations. So the random access memory is divided into several segments. I mean, most of the cases, the instruction or the data which is stored in the RAM is normally erased when there is some power interruption. So in order to back up some portion of the instructions, if a user wants to save the program, then if there is some battery backup, then that program can be stored for a specific period of time. On the other hand, in some cases, like it was discussed a little bit earlier, if the facility of EPROM is available, then the user can store the data in the program in the EPROM, so that the program doesn't have to be written each time the user is going to run the PLC. Now, regarding the input-output units, so through the input-output interfacing units, the external devices, input devices or output devices, can be connected with the board. So some of the input devices and output devices, some of the input devices could be the different type of push button switches, momentary switches, or static switches, different types of sensors or limit switches. And output devices could be LEDs, lights, motors, or different valves. Those have to be operated upon detecting any changes through any sensor. So in general, the input-output units offer the uh, uh, option for the user to connect different devices externally to the PLC board. So in terms of the block diagram, a PLC normally conventionally has some input ports and some output ports. So through the input ports, the user can connect different input devices, and through the output ports, the user can connect multiple output devices as well. So how many input ports and output ports are going to be there, that depends on the manufacturer. So along with the input ports and the output ports, each port has its own designated memory address. For example, here, this particular port, its corresponding address is P00. Then similarly, from P00 to P07, 8 input ports are designated in this diagram. And for the output ports, from P40 and P47 up to this, 8 output ports are designated in this particular diagram. Now, how these addresses are annotated, that is dependent on the manufacturer. Different manufacturers use different annotations to indicate the address associated with a particular port. Now, this sort of addressing is normally used by the in the PLCs which are manufactured by LG. Now, in our hardware lab or in the machine lab, we have a PLC board that is actually manufactured by actually a subgroup of LG, which is LS. So from that group, they produce a PLC of which they have termed as XGB series. So within that series, the board that we have in our hardware lab, that has a model of XPCDN20. So for this XGB series PLCs produced by this LS brand, those follow these sort of annotations for the input-output ports. So P indicates that, by P they indicate any physical ports. So these input-output devices are physical ports where the user have the authority to connect any input-output devices. So for addressing these input-output ports, they start the address with P, and then the corresponding numerical digits associated with the address, for example 0000. So they designate the address in hexadecimal, although it is written over here as P00, but the actual address is P0000. So and up to P1023F. So from starting from P0000 up to P1023, these memory locations are allocated for the input output devices. So whenever the user is going to write a set of instruction using the ladder diagrams in order to indicate a particular input device or an output device, the corresponding address of the port has to be used to establish the relation between the input output devices. Now, how the input output devices are connected externally to the PLC board, that is represented in terms of this diagram. So this left hand side portion represents how the input devices can be connected, and the right hand side portion, it designates how an output device can be connected externally to the board. Now, as you can see in this figure, as an input device, a normal switch is considered over here, a push button switch. So one terminal of the switch is connected to the port, the other terminal of the switch is connected to a power supply, and from the power supply the connection is completed through the common terminal. So for this particular diagram, it has been hypothetically considered that all these input ports have only a single common terminal. So connecting any other input devices to other ports will also have a similar way of connection. So as you can see in the second port, if you want to connect another input device, so one terminal of the input device should be connected to the port, the other terminal should be connected to the power supply, and the power supply completes the path for current flow through this common terminal. Now obviously internally there should be some connection between these two ports internally, that I will try to show you a little bit later how the path of current flow normally is completed. Now similarly for the output port also, the connection can be done in similar way. One of the terminals of the output load has to be connected with the output port, and similarly the connection has to be completed through the source to the common terminal. In this way, multiple output devices can also be connected, and if the output port is capable of handling AC supply, then instead of a DC supply, an AC supply can be also, AC loads can be also supported through those output ports which are capable of carrying AC signals. Now this diagram shows how the devices are connected externally. Now let us consider the internal configuration of input port and the output port separately. So this is showing an internal configuration of an input port from the port up to the common terminal, how they are connected internally. If you remember the diagram of the internal architecture, you'd remember that the inputs are passed towards the internal circuits or the CPU, first of all through the optocoupler. So here is the optocoupler, how it is connected between a particular port and the common terminal, and each separate port has a corresponding optocoupler connected to it. So here we are only showing for the first port P00, and this type of configuration is actually for handling DC inputs. So for this port P00, let's say if we consider that an operator has pressed this push button switch, the switch is now closed. So when the switch is closed, there is supposed to be a current flow through this port that is going to come over here, and it is going to cause this particular LED to turn on. And when this LED is turning on, the LED is going to emit some light towards the phototransistor, and the phototransistor is going to conduct current from its collector to emitter. And this VCC, this supply voltage which is associated with this phototransistor, that is going to provide the necessary current towards the CPU or the other internal units. So normally the input devices that are connected with uh, the PLC that we have in our lab, the rated voltage of those input devices are 24 volts. So using a 24 volt DC supply, those input devices are triggered. Okay, just a minute. So the input devices are such that they up to 24 volt supply, the input switches or sensors that can handle up to 24 volts DC source, they can be connected as the input devices for this PLC that we have in our hardware lab. However, the 24 volt supply is normally way more than the rated voltage of the internal circuits or the CPU or the microprocessor, because maybe the microprocessor needs only 5 volts to operate. So the optocoupler actually separates this 24 volt circuit portion from the internal CPU, and the CPU is actually powered through the 5 volt signal that is associated with this phototransistor of the optocoupler. So although the input devices are carrying a higher voltage, once they are actuated, the corresponding signal is sent to the CPU in terms of a lower voltage level to carry out a specified instruction uh, stored by the user. Now, apart from this optocoupler, a status indicator LED is also associated with each port. So suppose for this port P00, a status indicator LED is supposed to be there, which is going to be visible at the top of the PLC board. So when this particular port is receiving any signal, this status indicator LED will glow. So from the external side of the board, the operator can see that which ports are receiving signals. Now, for input port, in order to support AC signals, there has to be a slight modification in the internal configuration, which is that between the port and the common terminal, a bridge rectifier should be there, which would rectify the AC signal and sends the corresponding DC output from the rectifier towards the optocoupler, and the rest of the portion is actually same. So like I said, that for the physical ports, the XPC PLC that we have in our in IoT, so they address the physical ports starting from P, then suppose P00 in this way. So in general, we can say that after P, we will have some numeric digits or hexa digits. So in general, we have just denoted it here as PXX. So along with that, a status indicator LED should also be there, which would indicate whether this particular port is receiving any signal or not. Now, if we consider the internal configuration of the output ports, so there could be three possible configurations. The first one shown over here is the relay type. So in this relay type configuration, between a particular output port, let's say for this case P40, and the common terminal, in between them, the internal connection is done in the form of a relay, an electromagnetic relay. So when the CPU is sending some signal for actuating some output, that signal is going to energize the coil of the relay, and when the coil of the relay is getting energized, it is going to make or break the associated contact. So for this case, the normally open contact is shown. So when this coil is going to get energized, this contact will close, and the corresponding current will start flowing through the load. So as this is a mechanical device, electromechanical device, the contact is a mechanical type of contact. So this relay type internal configuration is capable of supporting both AC signal and DC signal. So both AC and DC loads can be supported by the relay type output ports. Now, apart from the relay type, the output port can be configured using a transistor, where a specific output port and its common terminal could be connected through a transistor. So in this case, an NMOS is shown over here. So this is the drain, this is the source, this is the gate of the NMOS. So when the gate signal for the NMOS is going to be coming from this optocoupler. So when the optocoupler is sending some signal to the gate of the MOSFET, upon getting sufficient gate signal, the MOSFET can draw currents from its drain to source. So once the MOSFET is triggered, the MOSFET can, result in the current flow through the load, and the load can operate. But in this case, the operation is supported for only DC loads, because the transistor can, provide current or direct current into only one direction. So this type of configurations of output ports will enable the user to only use DC loads to these respective ports. Now the third type of configuration could be using triac. So just like before, the only the difference from the previous slide is that the transistor or the MOSFET is replaced by a triac. So the gate signal for the triac is going to come from the optocoupler, and as the triac is a bidirectional device, so it is capable of handling AC loads as well. Now, this is more like how a hardware PLC board would actually look like. So at one side of the board, you would have some input ports, and at another side, you would have some output ports. So let's say these are the inputs, these are the outputs. And how the hardware wiring is done between the input ports and the input devices, that is indicated in this particular figure. So if you zoom in, you will see that each port is, and its corresponding address is designated in on top of the board. So for example, this particular input port, its corresponding address is P00. Then this corresponding port This corresponding port is having an address of P01. Similarly, the next port has an address of P02. So each input device connected with the particular port has to be designated with this corresponding address while the user is writing some or developing some program. Now, if you look at the connection to each input port, you will see that the connection is similar to what was shown in the block diagram a few slides earlier. So one of the terminals of the input device is connected to the port, and the other terminal is connected to a DC voltage source. And this path is completed by connecting the other terminal of the DC source with the common terminal. So here, this is the common terminal. Now, the polarity of the DC source, you can see that the diagram is indicating that you can connect the DC source in both the positive polarity and the negative polarity. So, according to this diagram, okay, you can suggest that that would be actually not a problem in this case if this sort of an internal configuration is there, because if you change the polarity, instead of connecting the DC source in this manner, if you reverse the polarity, what will happen is that instead of this LED is going to turn on and this LED is going to emit some light. So even if you change the polarity of the DC source, it will not hamper the operation of a particular input device. Now, along with the input ports, as I mentioned earlier, that each input port is supposed to have some status indicator LEDs. So these are those status indicator LEDs. So if any one of the input ports is getting a high signal, their corresponding LEDs will glow. And from the top of the board, the observer can have an idea that which ports are functioning. Other indicator LEDs are whether the power supply is on or not, whether the PLC is running a specific code or burning a specific code or not, whether there is any error. Though for indicating those, some other status indicator LEDs are there as well, and some LEDs are there to indicate the status of the output ports. So these ports on the bottom hand side, we have the output ports. Now this port P40 is this one, P41 is this one. In this way, the addressing of each output ports are designated. Now, one thing you can see if it is zoomed in, like this, and this the wiring which is shown for the output ports. You can see in the previous diagram I had shown you that all the output ports are having a single common terminal. However, normally the PLC ports offer separate common terminals for some specific output ports. For example, for this case, this P40, it has a designated common terminal COM0. P41, its designated common terminal is this one. For P42 and P43, they have a single common terminal, that is COM2. So in actual case, several output ports share a common terminal, but there are multiple common terminals. So can anyone suggest what is the possible advantages of having multiple common terminals available at the output side? ID 35.
Yes, sir.
Can you suggest what advantage we can have if we have different common terminals associated with different ports?
No, sir.
Anyone else? Okay, let's say instead of having a single common terminal available to us, let's say for these ports we have a common terminal COM0, and for these three ports we have another common terminal COM1. Then what possible advantage we can get is all these four ports, at these four ports we can run some loads at a specific voltage level, and for the other ports we can run those loads at a different voltage level if it is necessary. For example, a particular load connected with P40, let's say we are powering it up with a 24-volt DC source. We're completing the path using COM0. Now what will happen if we want to connect a motor that requires say 100 volts to operate? Then as we are already connecting a load which is operating at 24 volts, and all these other four ports also share the same common terminal, it is not possible to connect this motor to any one of these ports because the common terminal is already having a supply of 24 volts, so another supply of at a different voltage level cannot be connected with any of these particular ports. So for that, any one of these three ports might be used where the motor can be connected and it can be operated at a higher voltage level. So if it is necessary to operate multiple output devices at different operating voltages, so having separate common terminals for specific ports might be useful. So all the devices which would operate with 24 volt range, they can be connected in any one of these ports. And if there are multiple devices that require 100 volts for operation, they can share this common terminal along with this any one of these three ports. Even if some loads are DC in nature, some loads are AC in nature, then separate ports can be used with their designated common terminals uh, to do the necessary connection to make them operable. Now, how the connection of the input device and the output device is done.
Sir?
Yes.
If I may understand, like these different commands at the output, they are there so that if different devices are to be connected, they can be connected on separate commands.
Well, I said that if different devices are or different output devices and their rated voltages are different, then you cannot use the same common terminal to connect different voltage levels. For example, like it is shown over here, some output devices, maybe their rated voltage is 24 volts. They require a 24 volt DC source to operate. So once you use any one of these ports, suppose these 5 ports share a common terminal COM0, then once you connect a load with 24 volt supply using any one of these ports and this common terminal, then for using any other one of the other 4 ports that share this common terminal, you cannot use them to operate a device that requires higher or lower operating voltage, because already this common terminal has been connected with a source of 24 volts. So any device which requires similar operating voltage, you can connect within these output ports. And the other available ports which share a different common terminal, that can be used to operate a device at a different operating voltage. For example, I mentioned it is not exactly like what you'll find in a hardware board or physical board. Just hypothetically, I'm saying that uh, maybe these 3 ports share this particular common terminal. So any one of these 3 ports you can use to operate another load which requires a higher operating voltage, and you can complete the connection with their respective common terminal. So in this way, at the output side, having multiple common terminals designated to separate output ports will allow you to operate multiple devices at different operating potentials or operating voltages. Now, 2 terms I'm going to mention over here, that is sourcing and sinking. So these 2 terms are often used by the manufacturer to indicate what type of connection you can make to a particular input port or a particular output port. So first of all, if we consider about input ports, then there could be 2 types of connection. One is called the sourcing connection, and another type of connection is called the sinking connection. So let us focus on figure A first. So for this figure, let's say this is the input module internal to the board, and this is a input switch connected to a particular port, and this is the common terminal, and between the port and the common terminal a supply is this supply is there. So for this particular configuration, the current is supposed to flow in this direction as the arrowhead suggests. So considering the direction of the arrowhead or the direction of current flow, it can be said that the current is flowing from the input module towards the switch. So as the uh, input module is sort of pushing the current towards the switch, it can be said that the input module is here working as the source, or it is sourcing the current towards the switch. And as the switch is receiving the current, it can be termed as the sink for this type of configuration. So here, as the input module is sort of acting as the source, it is this sort of connection is normally called the sourcing connection at the of an input port. On the other hand, if the connection is done in this manner, where the current flows through the switch towards the input module, then the switch is, or the input device is passing the current towards the input module. So the input device here is sort of acting as the source, and the input module is acting as the sink, or it is receiving the current. So as the input module is sinking or receiving the current, this sort of connection is called the sinking type connection. So the manufacturer normally defines whether a particular device should be connected as a syncing type or a sourcing type at the input side. For example, if I go back for this type of a configuration of an optocoupler, both sourcing type and syncing type connection can be done because there are two LEDs present inside the optocoupler. So depending upon the polarity of the DC voltage source, the current can flow in both directions, in the clockwise direction and also in the anti-clockwise direction. So the input module may work as the source or it may work as the sink. So this type of internal configuration gives the option of connecting the input device either as in the source type connection or in the sink type connection as indicated over here. Now regarding the output module, similarly for the output module as well, the manufacturer specifies whether the output device should have a source type connection or a sink type connection, and the convention is also similar if the direction of current flow is such that the current is passing from the output module towards the output load, then the output module is uh, considered as the source, and this type of connection is called the sourcing connection. And if the current direction is such that the load is passing the current towards the output module, then the output module is working as the sink. So this type of connection is called the sinking connection. Now for this is let's say for this type of connection where we have an NMOS in the internal configuration of an output port, then what type of connection is this one? Is it a sourcing connection or a sinking connection? Which one is this one?
The sinking.
Yes, because the NMOS can only drive current from the drain towards the source. So if the direction of current is considered, so current is getting transferred from the load towards the output port. So the output port here or the output module is working as the sink. So this is a sinking type connection. However, let's say the manufacturer hasn't used an NMOS, they have used a PMOS. So if they had used a PMOS, they would recommend in their datasheet that while the user is connecting an output device, the connection should be made as a sink type connection. Sorry, a source type connection. Because in case of PMOS, the current flows from the source to drain. So in order to make the current flowing from source to drain, in case of PMOS, the polarity of the supply voltage would also have to be reversed to apply a positive potential difference between source and drain, and that would ultimately cause a current flow in the clockwise direction in case of PMOS. So in that case, the current direction will change and the output module will work as the source. So depending upon the internal configuration of the input module or the output module, the manufacturer will specify in the datasheet whether the user will be capable of doing both source type connection or sink type connection, or only one type of connection the user has to follow. And also a specific output port, for example here for showing all the three output configurations such as the relay type, the transistor type and the triac type, I have used this particular port P40, but this single port will not be able to have all the three different types of configuration at a time. Just for illustration purpose, I have shown it like this, but in general, a particular port will have one of these three types of configurations, and which type of configuration it has, it will be also mentioned by the manufacturer. So a user, while using a particular PLC, has to see the data sheet to have an idea that which ports can be used for only DC supply, for which ports the user can connect AC loads. So for this, the manufacturer data sheet has to be followed by the user. Now, regarding the communication unit, so different communication serial communication ports are normally available along with the board or integrated into the board, so that communication between the PC, the computer, and the PLC can be made, so that the program can be written into the PLC. And also the communication between other peripherals, if necessary, those communication can be established using these ports. So the commonly available serial ports into the PLC board are the mini DIN or PS2 ports, which are actually similar to the ports that we used to use to connect our keyboards or mouse previously. Later on, all of them have been nowadays replaced with the USB ports. The other type of serial port could be the USB mini B. So using this sort of port also, we can establish connection between the PLC and the computer. So you are also familiar with USB mini B type of ports. The earlier mobile chargers used to contain this sort of ports. Then other serial ports could be there, the RS-232 or RS-8 485. So among the serial ports, among these three, this is the most oldest. Compared to this, these mini DIN ports are uh, uh, ports were invented later. Those were later on replaced by the USB ports, different types of USB ports. But mainly this type of serial ports are available in the PLC to establish communication. And the general purpose is to upload the program from the PC to the PLC board, or if it is necessary, to connect other peripheral devices, and device verification, data synchronization between user applications can be done through the available communication ports. And many PLCs also contain Ethernet port. So using the Ethernet port, different PLC ports can be interconnected. So by connecting different PLC boards, a sort of local area network can be formed. So information or data from one PLC board to another PLC board can be transferred, and some other function can be carried out in the other PLC. And maybe a particular PLC board has a minimum number of input and output ports, but the control system requires large number of input data to be processed. But if a particular board has only a limited number of input ports, then by connecting multiple PLCs using the Ethernet ports, the data processed by one PLC can be transferred to the other PLC, and some inputs which input data which is taken by the other PLC, that can be processed along with the data received from the first PLC. And apart from the Ethernet port, also the PLC, most of the PLCs are modular designs, so you can add extra modules with the board in order to increase the number of input output ports, or the uh, I mean uh, uh, adding additional memory, or like this extra modules are available, or some driving modules for running a specific type of load. So most of them are normally modular designs. So for today's class, I intended to discuss up to this. So if you have any question, you can ask.
Hello, sir.
Yes.
Sir, the ports we use in our PC, HDMI ports, what type of are they, sir, based on the considerations we have studied today?
HDMI port is a different type of port that is not, I mean, that doesn't resemble any of these three ports, right? So they are even I mean more recently developed ports. So whether they are for serial communication or parallel communication, I am not sure about that. But the VGA port, the HDMI port, those are different configurations. So some of the common ports which are available in the PLC that I tried to highlight over here.
Okay, sir.
Sir, in the Ethernet cable, we know there are different categories of Ethernet cable, and each category introduces a maximum support length, different maximum support length or data rate. So I was asking that how this data rate is increased in every category. I mean, there is a same element to construct the Ethernet cable. So how do we increase the data rate in that element or the maximum length? How do we increase this parameter?
Well, maybe the question you were asking, it is more like an expert of communication background might be able to answer that particular question, that how to increase the data rate, because I am not that much familiar with the internal configuration of the ports or any one of these ports, how the data is actually getting transferred. So but I know that some of the ports support half duplex operation, some of the ports support full duplex operation. So for the ports which support half duplex operation, so they can only transfer data in one way. I mean, while they are transferring the data, at the other side, the receiver has to wait until it finishes receiving the data. Until the data is received on the other side, then the device can send some data from its own side in the half duplex operation. But in the full duplex, both the devices, interconnected devices, are capable of transferring data simultaneously. So in that way, in some sense, the data rate can be increased. I mean, when both the devices is able to transfer data simultaneously. But specific for Ethernet port, how the internal configuration can be changed in order to improve the data rate, I don't have much idea about it. Maybe a teacher who is expert in communication or the internal configuration of these ports, a better idea you can get a better idea from from them.
Yes, sir. Thank you.
Okay, I think no one wants to ask any further questions. So I'm concluding today's session.